Now let us look at methods for measuring polymer characteristics, methods to measure these characteristics during the reaction, reaction kinetics, and some applications. Polymer characteristics. The first one I will be talking about is molecular weight. As we know, the individual polymer chains rarely have the exact same degree of polymerization and mass, and there is always a distribution around an average value. Hence, the molecular weight distribution relates the number of moles of each polymer species and the molar mass of that species. Different techniques are used to measure different averages of molecular weight. For example, osmometry measures number average molecular weight, light scattering measures weight average, whereas viscometry measures viscosity average molecular weight. The most common technique for measuring molecular weight distribution is size exclusion chromatography. And I show here a typical setup of this technique. As you know, is based on separation by size. Large particles elute first, small particles enter the column pore gels and elute later. So basically you have a HPLC pump, then the injector and chromatographic columns where the separation occurs, and then a chain of detectors such as light scattering, viscometer, refractive index detector, and UV detector. All these provide polymer absolute molecular weight based on direct measurements or approximate values based on the relationship between hydrodynamic volume and molecular weight of known species. As you know, molecular weight distribution by light scattering provides an absolute determination and no calibration is required. As I said before, we measure different averages of the molecular weight distribution, and they are introduced below. Number average, weight average, and Z average mass distribution, molecular weight. Another important polymer characteristic is dimension, and our techniques are focused on both hydrodynamic radius and radius of gyration. Shown in this slide are the definitions and also the relationship between the RH and RG for a hollow sphere, for a solid sphere, and for a random coin polymer. Now, how do we measure these polymer characteristics? By light scattering, viscosity, within size exclusion chromatography, and by combined measurements. Measuring monomer characteristics to determine conversion during the reaction involve spectroscopic identification of monomer concentration by UV, Vis, near-infrared, mid-IR, or Raman scattering. Another technique is using refractive index identification of monomer concentrations. Conductivity for monitoring conversion of the charged monomers. Light scattering. We use static light scattering, which measures total intensity of the light scattered and can yield molecular weight, virial coefficients, and radius of gyration. And we use dynamic light scattering, which autocorrelates scattered intensity fluctuations, usually to determine polymer and colloid diffusion coefficients, from which equivalent hydrodynamic diameters can be determined. Electrophoretic light scattering can make use of Doppler shifts and other features of light scattering from particles in direct motion under electric fields to obtain electrophoretic mobility and zeta potential. As I said, and show for better visualization in the graph on the right, static light scattering measures the average total scattered intensity at any given scattering angle, and it typically yields molecular weight, virial coefficient, and radius of gyration. Dynamic light scattering autocorrelates fluctuations in the scattered intensity due to the polymer diffusion, and it gives hydrodynamic radius via Stokes-Einstein equation. This is a typical light scattering setup for multi-angle light scattering detection and dynamic light scattering. Now, if we introduce Rayleigh-Debye Zim scattering, the size of such scatterers is typically bigger than 10 nanometers. Light is scattered preferentially in the forward direction, and interactions are taken account of with the second virial coefficient A2. A main equation is, as everybody knows, Zim equation, and for within approximations for small RG, we can use it for determining polymer molecular weight and virial coefficients. As you can see here, regardless of the polymer shape, sphere, coil, or rod, in the Zim regime, the form factor is independent on the shape, which allows us to use Zim plot and Zim approximation in order to determine molecular weight of the polymer. And shown here, it's a typical Zim method which uses discrete points and allow obtaining molecular weight, virial coefficient, and RG. Another way to do this, it's a continuous Zim method. Here the polymer concentration is ramped continuously, so no samples are made, no errors are introduced, and molecular weight of the polymer, virial coefficients, and other features are obtained automatically. An example is shown in the figure on the right for a polymer sample in aqueous solvent. In order to measure polymer characteristics such as dimensions, we use SEC, and shown on the left is radius of gyration for a charged polymer in different ionic strength solvents. And we can see here the effect not only on the slope, intercept, but also on the coefficient. The coefficient here gives us information about the structure of the polymer. And you can see that the polymer is totally neutralized at high ionic strength. You see Mark Wing coefficient for a random coil, whereas at low ionic strength the molecules are more rod-like. DLS measurements provide hydrodynamic radius, and in the graph on the right is shown the effect of the temperature on the particle size for a stimuli-sensitive copolymer. As you can see, the size decreases as the temperature is increased.